working towards sustainable mobility and the CEO of Mercury Cybersecurity protecting the world with quantum cybersecurity. So that's a mouthful. So first we're going to have a talk, and this will be followed by a discussion. So please enjoy the talk here tonight, and then ask questions at the end. Thank you very much. Let's give a round of applause to our talk.
I mean, the talk could be entitled Buzzword, Buzzword, Malta Sleep into Buzzwords. But we'll try and disentangle all of that. So, thank you, Danielle. It's just to clarify, it's not the first Nobel Coffee tonight. It's the first Nobel Coffee Day for 2024-25 season. For the season, yes. Because it's like my fourth one, I think, at this point. Yeah. Anyway. So I'm Andre, as Danielle just said, and I have a foot in quantum mechanics and a foot in cybersecurity, amongst a few other things, children, miscellaneous things in my life. And I thought I'd kind of bring the nexus. Basically, combine these two ideas together, share a bit about what quantum mechanics is, how it can help us improve computers, how it can actually destroy our cybersecurity, and kind of counterpoint to that, how we can create quantum-powered security, quantum-powered secure communication, which kind of solves the problem that quantum itself creates, so to speak. Hopefully we'll get through this with maybe half an hour. We'll see. As usual, please stop me by saying anything that's unclear. If you don't agree with something I say, if I'm not looking at you, throw something at my face, I will turn around. We can discuss. I'd rather have a dialogue than a monologue. Last thing is, I haven't slept for 5 years, so please be kind. I've got dark circles about 3 right now around my eyes. Okay. Oh, and yes, if my voice gives out, I lost my voice yesterday, regained it kind of this morning. I gave a 2-hour lecture, so it's kind of iffy. I refuse to use a microphone just because it really bothers me to speak like that. But we'll see, okay? So if my voice gives out, then I might speak like that, and then live stream will not hear it. But we'll see, okay? Right, okay, so let's start by kind of diving into some of the ideas of quantum mechanics. So I'm going to keep the slide on the theory, obviously there's no mathematics, light on the ideas, but kind of just sprinkling in a few ideas, tying them in together, and then hopefully coming up with something which connects quantum mechanics to something which many of you will be familiar with. That's the idea. The idea is not to do a deep dive in anything today. It's almost 7:30 on a Tuesday. No one wants to do a deep dive in quantum mechanics. Right, so I'm going to start off like, okay, if this thing changes. Oh, there we go. I'm going to start off with one of my standard slides. This has been a staple of all my Cafe Science talks, I think, plus most of my other talks. And this is, for those of you who don't know, that's Richard Feynman, Nobel Prize winner in 1980 something, if I remember correctly. But fabulous, fantastic mind, brilliant physicist, made some really, really big contributions to quantum mechanics. But he was also a fantastic teacher. And those of you who are studying physics or are interested in physics, there is something called the Feynman Lectures on Physics, given in 1964, but timeless. So buy the books, they are really, really good. They cover literally all of physics from the ground up in one fell swoop, from kind of the voice of one person. And in the Feynman Lectures, I don't know which chapter, but when he's talking about quantum mechanics, keep in mind, this is closer to the birth of quantum mechanics than it is to the present day. He writes, there's a whole paragraph which I'm going to skip on purpose. He writes, or he says, I think I can safely say that nobody understands quantum mechanics. Which sounds like a very provocative statement. But the important thing is to understand what this means and the context behind it. Because what this means and the context behind it is as valid now as it was in 1964. And what it means is quite interesting. He's not telling us that you or I are too dumb, our IQ is not high enough to understand quantum mechanics. After today, you might have some impressions about me, negative or positive, but in general, he's not saying that. What he's saying is something very different. What he's saying is that quantum mechanics, if you try and understand it, if you take it seriously, if you kind of go through the mathematics and really internalize the mathematics and say, this is how I understand the universe to work, you'll realize that it runs almost in direct opposition to our intuition. And we might understand the mathematics, we might have a certain set of rules to get from the mathematics to how we expect an experiment to behave, and it's those rules that we can verify. But why the mathematics has that structure, why the universe obeys those rules, no one really knows. No one knew back then, no one knows today. We might know a bit more, as humans do. We generally get to know a bit more as time goes on, although if you browse X these days, people seem to know less than we did 2 years ago. But anyway, I'm growing old and cynical, sorry. Permit me my indulgences. And, so we do know a bit more, but we're still not yet fully kind of in tune. We still don't fully understand why the universe works like this. So what I'm going to ask you to do is suspend this belief. So there are certain parts of what I say which do not make sense. All I can tell you is everything I say is backed up by years and decades of experimentation and many decades of mathematics. That's all I can say. I can't convince you that what I'm about to say makes sense, because if you haven't seen it, if you haven't run the experiments yourself, then ultimately maybe you don't believe me. But I'm going to ask you to suspend that disbelief today. Okay, so take what I say in the spirit of no one understands quantum mechanics. So maybe what this guy is saying is also correct. Or just enjoy it, please. And to understand some concepts, I'm going to introduce one of the most basic things I can think of. Okay, so for now, let's throw quantum mechanics out of the picture. We'll come back later. And I want us to think about that box. In computer science, this is kind of what is called a black box. And it does what it says on the tin. It's a box which contains some sort of device inside it. Now, the device is not a magical device. It could be, I don't know, a circuit board. It could be a few wires connected together with a battery or something. It's some sort of device that we know how to build and control. There's no magic, there's no mystery about it. And it could be a well-trained monkey, which always kind of does the same thing. Yeah, could be whatever it is. Okay, but it's some sort of black box. And I am not allowed to peer into the black box. I'm not allowed to open it to investigate and how it works. Okay, but I'm allowed to somehow interact with it. And I'm going to introduce, I have two ways of interacting. One is I'm allowed to give some input to the box. There's a switch. I put the switch on, that's one kind of input. Switch the switch off, that's another kind of input. In computer science, that means I have a 1 bit input, 0 or 1. But you can think about it as two different kinds of inputs. That's two different kinds of inputs to my fabulous box. Okay, so maybe one input will cause it to perform some kind of calculations, the other input will cause it to perform some other kind of calculations. Okay, so this is what I mean by input. That's how I get data into the box. Getting data out of the box requires output. And my output is simply a light bulb or energy efficient LED, because we're all about green these days. And the LED is either on or off. So I set the switch to on, the machine works, and gives me an output. The output will be on or off. Set the switch to off, machine works, the output will be on or off. So there's a means for me to feed data to the machine, and a means for me to get data out of the machine. Are we all clear? All happy? Okay, now, if you think about it, if we exclude kind of magic and crazy stuff, and if we constrain ourselves to things we can build with circuits and computers and simple things, there's actually only 4 different kinds of device, 4 different kinds of box that I can have. And we can actually run through them very quickly. So the first version has the following properties. When the switch is on, the light bulb is on. That's right. When the switch is off, the light bulb is on. Okay, that's one version. Now, I don't really care what happens inside. It could be a supercomputer calculating something crazy, or it could just be that the switch is wired to the light bulb. It can be that simple. Okay? So we don't really care what's going on inside. We just care about what we're doing and what we're getting back. So that's version number 1. Version number 2 is the opposite. Switch the switch on, light bulb is off. Switch the switch off, light bulb is on. Okay, so these 2 versions are kind of related, they're opposite each other. That's 2. Then there's another 2. One is where the light bulb is always on, maybe it's just always connected to the power. And one is where the light bulb is always off. Maybe it's always disconnected from the power. Or maybe it's the result of a calculation which always gives us 0 again. Okay, so we can think about this in the most creative way possible. But I hope, and those of you who are not convinced, go home, do some homework. I hope I have convinced you that these are the only 4 different possible versions there are. Everything we can think of, as long as it excludes magic and crazy stuff, will fall in one of these 4 categories. Now I presented them in a particular order because there are actually kind of 2 groups of 2. There are actually 4 really. Let's go back through them. There's this one and this one. And I'm going to call those balanced because there's as many bulbs which are off as there are bulbs which are on. Okay, so kind of there's a balanced mix of light bulbs. So there's 2 which are balanced, opposite each other, and 2 which I'm going to call constant because they're constantly on or constantly off. Okay, so there's 2 balanced and 2 constant versions of the box. So far so good? Okay, now I'm going to play a game. And the game I'm going to play is, I give you one of these boxes, you're not allowed to look inside it, and the question I ask is, have I given you a balanced box, or have I given you a constant box? And again, you can think about this, but there is no faster way to answer this question. The only way to answer this question is run the box with the switch in the on position, look at what's happening, run the box with the switch in the off position, look at what's happening, and then check, has the light bulb switched on or off, or has it remained the same? Do we agree? Okay. And let's assume that nothing in life is free, and so is this box. Every time I run it, I will use electricity, use some energy, time, money, whatever. Okay, some resource. Okay, so all I've said basically can be paraphrased as it will take us twice the amount of resources to answer the question which I posed as it does to run the box once. Do we all agree? That's kind of the most efficient way of answering the question. At least in a non-quantum way, okay? And the point I'm trying to draw eventually, or get to, is that if we allowed ourselves some quantum stuff, then things could be done more efficiently. But it's one step at a time. Okay, so if we only had a classical box with one switch, we would have to run it twice and then get the result. And it so happens that if you had 2 switches, you would have to run it more than twice. If you had 3 switches, you would have to run it even more times. And actually, the number of times you need to run this machine, the amount of resources you need, grows exponentially quickly with the number of switches. In other words, in plain English, it grows really, really quickly. It blows up. Which makes things very bad. So how can we make the situation better? And one way of making the situation better is to kind of try and see what we can improve upon this. Now, as it is, there's nothing which can be improved. There's a switch, there's a bulb, there's a box. What can I improve about this? Not so much, but let's kind of look at the most basic of these components. So let's think about that little switch over there for a second. Now, I'm a physicist by nature. I'm not by training, rather. I'm a human being by nature, I guess. I'm a physicist by training, not an engineer. So all of this stuff, that's just additional complexity which I don't need. So really, what I care about is not so much what the switch looks like or what the color of the label is or whatever. What I care about is that the switch has 2 positions, tick and tick. And I can assign labels to those positions. So I'm going to call on 1 and off 0, kind of mimicking what computer scientists do. And that's all it is. I mean, for me, all a switch is just something which lives in one of those 2 dots. It's either there or there. Right? Does this make sense? Okay, so that's that's where we are. And in fact, you can actually kind of describe everything I've said about this black box and resources and everything, starting from this kind of mathematical model where the switch is simply kind of one of those 2 points, and then you proceed, and everything works out, everything checks out. Now here's where things get a bit strange, and where I asked you in the beginning to kind of suspend this belief. Because as anyone who's done any geometry knows, if you're given 2 points, any 2 points in 3-dimensional space, so long as they're not the same point, if there are any elements here, if you're given any 2 points which are not the same in 3-dimensional space, you can draw a sphere, of which those 2 points are kind of the North Pole and the South Pole. Yeah, that's fun. It's a nice piece of geometry, but what meaning does it have? Well, the meaning it has is rather strange, but bear with me. The meaning it has is this: if we allow our switch to exist not just in the realm of what I would call classical physics, the physics of the ordinary around us, but in the realm of quantum physics, it turns out that the switch can exist not just at those 2 points, but literally anywhere on that sphere. Okay, so there's a very real sense in which I could have the switch sitting kind of at the equator of that sphere, being 0 and 1, shall we call it. Okay, we're not going to go through the mathematics here. And this either makes absolutely no sense to you, or you might think, well, isn't this the same as, are there any switches around that I can play with? No. Okay, those are connected to things, so I should know. Yeah, okay. So you might either think that this is obvious, or that this doesn't make any sense. Most of you who would think that it's obvious are probably, if I'm so bold, associating 1 and 0, 0 and 1, with the idea of having a switch, which I'm kind of constantly switching between 0 and 1. So it's sometimes 0 and sometimes 1. Are there any electrical engineers or engineering people here? Possible multi-formulation, basically. Okay, so you might associate the idea of kind of being halfway between 0 and 1 as some sort of modulation, some sort of switching on and off constantly, so that it kind of averages out to being half the time in 0 and half the time in 1. But that's not the case. Okay, and this is what I want to discuss now. It's not the case. Those of you who think it makes absolutely no sense, fair enough. You're with the majority of the population here, so that's fine. But this is where I think to suspend this belief. We now know that we can actually create devices that exhibit this behavior. Now, what I'd like to do is just to motivate. Again, this talk is about motivating things. It's not about kind of working through the maths. I'd like to motivate the difference between how our brain sometimes processes something like 0 and 1, which is sometimes 0, sometimes 1, and the reality, the quantum reality of being 0 and 1 at the same time. Now, unfortunately, the metaphor of a switch doesn't really lend itself very well to this, so I'll have to switch metaphors for a while, and then I'll come back.
Can I just ask, you talk about a sphere, and it can be anywhere on the sphere. Couldn't it be, why do you need to bring the third dimension into it? Could it be anywhere on the circumference of the circle as well? Wouldn't that be simpler?
That's a very good question. It could be just on the surface, on the circumference of the circle, of course, but we're actually allowed to make use of extra information in quantum mechanics and actually look at the third dimension. So it just kind of emerges directly from the mathematical structure. It has an observable consequence. If I remember in a couple of minutes, I'll tell you kind of what the observable consequence is. It corresponds to a phase difference, but I can show visually what it means. So you don't have to, but if you're looking at the full richness of the structure, it's there. And just in case you're interested, this is actually called the block sphere, B-O-L-C-H. So if you Google that, you'll find any number of visualizations and explorations. So I'm not kind of simplifying anything. This is literally the model that we use. Of course, with slightly different notation, but it's there. So yeah, thanks for the question. So as I was saying, I want to kind of motivate what this 0 and 1 means, and I'm going to do that using a slightly different visual metaphor because not every metaphor works well in all situations. So let's go there first and then there.
How come it is a sphere, if I may? Why that to?
Okay, so it's what is the simplest way to answer this? So basically, watch this space. I have to think about the simplest way of answering this because I could easily say, you take any collection of vectors with unit length and it'll give you a sphere. a mathematical answer, but I can't come up with a good kind of non-mathematical answer off the cuff. I'm going to try and think about it while I speak. But like the mathematical answer is there is a mapping, a relationship between literally any direction you can take in space. And this, okay, actually we can talk about it. I'm going to use it this way. So there is a mathematical relationship between, and by relationship I mean like a dictionary, okay, so 1:1, between the state of this quantum switch qubit and a direction in 3 dimensions. And if you think about kind of a physical arrow which can point anywhere in 3 dimensions, and you make sure that the arrow has always the same length, let's say 1 meter, the shape that that arrow will trace is the sphere.
How does this mean the vectors are constant?
They have to be normalized because that kind of ties into the mathematical meaning of some things. But yeah, so normalization will give you a sphere. What gives you the sphere?
But in the past, I would visualize it as a probability graph, as an improbability state between the 2 points. Is that the correct way to visualize it, or?
If you think about it as a probability like between 0 and 1,
Yeah.
but the probability kind of, at least the way I understand it, is closer to the image of sometimes 0, sometimes 1. You have a finite probability of finding it to be in a 0 state, finite probability, this is literally 0 and 1 at the same time. And this is what I'm trying to kind of motivate with the next set of slides. Again, I mean, this is all motivation, it's all metaphoric, but it's keeping very close to the mathematics. So, and I think we're going to blow past the half-hour mark, but we'll see. We're still slide 11. What's slide 12? Okay, so how do we kind of visualize this idea of 0 and 1 being different from 0 sometimes and 1 sometimes? Imagine you have, and this is also one of my constant slides from the cafe side talk, so I usually have the thing. Anyway, so imagine I built a screen, no, not a screen like this, but like a metal screen, something which doesn't allow light to go through it, okay, an opaque screen. And I punched a hole, a rectangular hole, into the screen. Obviously, light will go through that rectangular hole, but it won't go through the screen, that's the idea. And I ask you kind of, what's going to happen if I shone light at that object? Well, light doesn't go through the screen, but it goes through the hole. And again, I hope that most of you will agree that you'll get something like this. Okay, it's a bit flat, but that's the only image I can find on it. But you know, light will go through. Excuse me. Light will go through where the slit is. Well, it spreads a bit, but these are details, and it won't go through anywhere else. Those of you who have very good eyesight will see that there are some lobes on the side. Let's ignore those, okay? These are details. Let's not talk about the details. We're talking about the big picture. Okay, so again, I have that thing, I shine light at it, light goes through the slit, doesn't go through anywhere else, and it gives me this kind of picture. Again, do we kind of all agree that this makes sense at least? Okay, so let me now complicate things a bit. I'm going to have this kind of situation, where I have 2 holes, 2 slits punched into my screen. And now, indulge me a bit. I'm going to call the first one, or the one on the left, 0, and the one on the right, 1. It's a bit like our switch. And again, if we just have 0, so if we just shine light through the first slit, well, we're going to see the same thing, right? Do we agree? If we just go through the first slit, yes. If we just shine light through the second slit, we're going to see the same thing. Maybe shifted a bit, but you know, same thing. What happens if we shine light through both slits at the same time? Those of you who have done physics will come up with possibly the correct answer. Those of you who have never done this experiment might not come up with the correct answer initially. Because our intuition might tell us, well, if I have one of these for each of the 2 slits, shouldn't I just get that? Okay, and this would actually happen if I were to sometimes shine my laser on the left, sometimes on the right, on left, right, and kind of go fast enough that it's half the time spending time there and half the time there. And I would actually get that. But I'm asking a different question. What if I shine light at both slits at the same time? And what you will actually see is that it's a completely different kind of pattern. And it's this difference, again, I'm not going to go into the details of this. It's this difference that I'm going to play on, which gives us our quantum mechanical superpowers. It's the difference between something which is sometimes here and sometimes there, and something which is both of them at the same time. Okay, so it's in this sense that that switch being on the equator, being 0 and 1, is fundamentally different from being half the time here and half the time there. Okay, it's not about averaging something. It's not about being sometimes and sometimes. It's being both at the same time. I don't know who was asking about the horizontal angle. Kind of this, was it you? Sphere as opposed to the circle. The third dimension, the angle around the third dimension, kind of shifts the dark fringes. You have a high frequency dark fringe there, and you kind of shift those laterally by going around the circle. If I'm getting the maths correct in my head. Okay, so it has an observable consequence, but it doesn't really matter, kind of broadly speaking. But it has an observable consequence. Okay, so there is a phrase, and I have no idea, I keep forgetting to look up who said this phrase, but there is a phrase that says more is different. This is kind of the thing I'm trying to get at here. By having these two different slits at the same time, by allowing our system to be kind of in this state of being more, we are fundamentally creating something which is different to what we would expect otherwise. Okay? And again, this is all metaphor. This is all a visual metaphor, but the mathematics runs very, very, very close to this. So, what happens now if we have a quantum? This is how we have a quantum. Right? What happens if we have a quantum black box or a system which has some quantum properties? Again, this is a part of the talk where I don't have time to go into the details. The only way to really kind of prove what I'm about to say is to go through the details, but we don't have time to do this. Although they are there on Wikipedia, those of you who are interested. But if we replace our ordinary switch, the one which could only sit at those 2 points, with a quantum switch, which is free to explore this entire sphere. And if we set the switch to be somewhere on the equator, and ran the box once, just the once, modifying nothing else inside, then in that one single run, we would get the answer of whether the box is balanced or constant. Okay? Now you might debate as to whether this is a useful question to ask or not. I'm not going to get into that debate right now. But the point I'm trying to say is by allowing our system to exist in a way which classical physics, the physics around us, doesn't allow us to exist, it can actually allow us to complete a task. In this case, twice as fast, or using half the amount of resources. What you can actually show is that if you have not just one switch, but many of them, n of them, you get what is called an exponential speed up. So with 2 switches, you go 4 times as fast. With 8 switches, you go 8 times as fast, and so on and so forth. So this is actually a scenario in which you can build a quantum device which solves a problem that a classical device can also, a non-quantum device can also solve, but it does so significantly faster. And this is kind of what I'd like you to keep in mind, that by allowing our system to explore these quantum states, we can create a situation where the technology works better. Everything else is details. Now, before I get to kind of some of the things we can do, it's a good idea to do a quick segue to have a look at or to understand that what I'm talking about, these technologies, these are not things which are 100, 200 years in the future. These are technologies which are pretty much on the cusp of being proper technologies as opposed to kind of lab curiosities. However, we're still at the early stages, so those of you who explore computer history in the 60s, 70s, and 80s, it was really exciting back then because we're discovering things all the time. It's the same with quantum tech at the moment. Literally every single day, something new comes along. Case in point, we have, at the moment, like 3, 4, or 5 different, completely different kinds of quantum computer, which we are, by we I mean, of course, the scientists in the lab, not me, no one trusts me with these things, but which humanity is exploring. Down on the left is a picture from IBM Labs, if I remember correctly, and it's based on technology broadly similar to what ordinary computers use, but brought down to almost absolute zero. And it's that temperature which allows these chips to manifest their kind of quantum behavior. Picture in the middle, that's an ion trap. So it's actually a system which traps charged atoms, but atoms, just suspends them in midair and keeps them there. I think nowadays they keep them there for months at a time. Literally, the same atom being there, stuck there for months at a time. And each of these atoms can be used as a quantum switch, as a qubit. Okay? So each of these atoms, which you're not seeing there because they're not in the picture, but each of those would be one of these quantum switches which I've been talking about. Then over there, the last one, that's a bit strange because it's a chip that uses light instead of electricity. Again, same thing, broadly speaking, you can use light as your quantum switch, as your qubit, and you can perform all sorts of interesting things. Okay, so again, just to give you a sense that these things do exist, you might not be able to buy one off the shelves at the moment, but they do exist, and they're coming to the market in, I would say, somewhere between 5 and 10 years, if they're not already there. But that's kind of me with the tinfoil on my head. Okay, so this is all well and good. Okay, with quantum mechanics we can achieve great things. Those great things are on the cusp of being achieved. But actually, can we do anything useful with this stuff, or is it just an interesting curiosity? And this is kind of the subject of the next few slides. So pardon me, I need to drink a bit because of my throat. I'm sorry, we know each other for so long, it's just natural for me to banter. Okay, so let me again motivate things bit by bit. Suppose I gave you the question, kind of, what is 3 multiplied by 70? Those of you who've done this particular sum in the past will just say, 51. But the rest of you will figure out a way of working it out. Maybe write 3 down 17 times, or write 17 down 3 times, and just add things together, maybe add the tens and then the units, whatever. There are different ways of doing this. But quickly, once you start doing this kind of thing over and over again, you'll figure out that A, the answer is 51. But B, it's actually quite straightforward to work out these kinds of questions. There are algorithms. By algorithms, I mean kind of a sequence of steps through which our brains, and even more so computers, can actually perform this computation quite rapidly. Change the numbers to something large doesn't really matter. Okay? I mean, we can run through massive numbers, even in our brains, and compute their products quite efficiently. And if you see some of the crazy things you find on YouTube of people being able to calculate these things, it is insane. But in general, there are ways of making this quite efficient. But what about the reverse of the process? What if I gave you that? I told you, break that number down into its prime factors, into the 2 numbers which, when multiplied, give us 323. The only way to do this is literally trial and error. Does 2 divide 323? No. Does 3, does 4, does 5, does 7, does 8, does 9, and so on and so forth. Eventually you'll hit on 17 and 19. Eventually it will work. Funny thing is, first of all, this takes a lot longer. Funny thing is, this kind of trial and error, and eventually you'll hit on the right answer, is exactly kind of the state of the art with our computers. There is no known way to do this, to perform this calculation efficiently on a computer, no matter how advanced the computer is. So if I gave you something like, whatever that number is, okay, it will take you, it will take me probably like 3 years at this point to work that out. But even ordinary computers will start slowing down and grow a lot larger than that. It will start taking years, thousands of years, millions of years for an ordinary computer to bring these numbers down into their prime factors. And that is actually what keeps the internet secure. But we'll get to that in a second. First, I want to show you something. What I'm showing here is, again, I forgot to put the attribution. It's taken from a paper from 2018 or so, maybe 2019. So horizontally, here, think of it as how big the number is, how big the number we're starting with is. Is it 323, or is it that massive number that we're talking about? Or is it something even larger, or something even larger than that? Vertically, we're talking about time. In other words, the question is, how long does it take a computer system to get a number which is that big and split it into its prime factors? And there's two sets of curves there which are relevant. One is this set here, which is kind of going to the moon. And that is, and of course I remind you, this is 2018. Things have improved since then, but broadly speaking, they're still the same. What that means is that if it takes a second to break apart a number with this many digits, simply doubling that will go from 1 second to 100 seconds. Double that, you go to a day. 10 years, 1,000 years, a million years, a billion years. Very, very, very rapidly. So even with the best supercomputers in the world, just doubling the size of the number increases the time it would take to break those numbers down from 1,000 years to a million years to a billion years. Or for all intents and purposes, it's not possible. It's just not possible in practice. In principle, it is possible if you could afford to wait for a billion years. You barely wait for 5 minutes in traffic these days. The other set of curves is different. It's these curves which, at least on this plot, look like straight lines. And those are different versions of quantum computers. Okay, these are not experimental results, these are theoretical results, but still. There are different versions of quantum computers running something called Shor's algorithm. And Shor's algorithm is actually the only known way to efficiently, quickly, break apart these kind of large numbers. But it only works on quantum computers. And in fact, you'll see that rather than kind of going through to the moon, as we increase the size of the number, yes, we need a bit more time, but it never kind of blows up. If you double the size of the number, you'll kind of double the amount of time you need, maybe 3 times as much. But it won't explode. Okay, and there's this fundamental difference, which leads to kind of one of the numbers I like to use, a quantum computer being 300 billion times faster at solving that particular problem than an ordinary computer, an ordinary supercomputer. And with 300 billion times, you're not comparing something fast to something slow. You're comparing something which could be fast to something which is, well, it just won't solve the problem. There's just not enough time in the world to solve that problem. Okay, so it's kind of fundamentally different. Now, how does all of this tie to cybersecurity? And I will speed up. Okay, so I'm not going to go through all the details. But let's imagine what happens when we have a situation with 2 computers, 2 people in 2 different buildings who want to communicate securely between themselves. Now, it could be me buying something off of Amazon, or it could be someone at the office of the Prime Minister communicating to Brussels. Okay, it can be something trivial or something very important, but the process is pretty much identical. That's perhaps one of the stranger things of life. And the process is quite straightforward. So I have that building over there with some computers, this building over here with some computers, and computer A wants to speak to computer E securely. And they do this by negotiating something called, it's an encryption protocol. I'm not going to go into the details. But ultimately, it is just a game of numbers. They're playing with numbers. So computer A sends some numbers to computer E sends some numbers to computer A, and they kind of manipulate these numbers in order to come up with something which is called an encryption key and a decryption key. And these 2 keys, all they are 2 very large numbers, one of which allows you to encode, encrypt, I don't know what other synonyms I could use, scramble a message, and the other which allows you to decode, decrypt, descramble the message. So all of this is done over the internet somehow, and usually we're none the wiser. But what is actually possible, and what we have good evidence that is happening at the moment, even without the tinfoil hat, is that when there's traffic between, for example, governments, traffic between data centers, high value traffic, what's happening is the following. People can actually sit between those 2 buildings. I don't mean literally between, in most cases it could be literally between, but between in the sense of somewhere on the internet along the data pipeline. So virtually between those 2 buildings. And it is possible to steal information as it's traveling from one side to the other. Now that information is encrypted, it's scrambled, it's hidden. And because of these things I was talking about earlier, it would take someone with even the best supercomputer a million years, a billion years to decrypt, to break into that data. But this thief is a bit smarter. He knows that in a few years' time there's going to be computers running Shor's algorithm, quantum computers running Shor's algorithm. So what is actually happening now is something called store now, decrypt later. People identify high value points on the internet, store the data, don't even try to do anything to it, and then wait for a few years to decrypt it. And what this has given rise to is a situation where we know that our communication systems are vulnerable to quantum computers. Quantum computers don't exist yet, but as soon as they exist, all the data which has been stored, let's say since last year, since today, since 10 years ago, suddenly becomes browsable, openable. And again, my data is not that important. In 5 years' time, everything I own will be expired, basically, including my credit card and everything else. But if you're talking about government level information, national security information, that takes a while longer to expire. So this is a threat which is actually really, really quite severe. Again, if you want more details, perhaps we can talk about them later. But there is a way to overcome this. So the problem that gives rise to all of this is the fact that with enough time, we can break into any communication system if we had access to a quantum computer, because it brings the million years down to a couple of minutes. So quantum is the problem. But it turns out that quantum can also be a solution, and this is something which I and my colleagues work a lot on, and something called quantum communication or quantum key distribution or some mixture of those words. And ultimately, what we do is we exploit the properties of light, the quantum properties of light. So, this quantum switch which I was talking about, you can actually encode that quantum switch in a pulse of light, a blip of light. So you send those switches, so to speak, Alice sends those switches to Bob. And by doing a number of clever maneuverings, a protocol, what Alice and Bob get at the end, we call it what they distill at the end, is a number which is the same at Alice's side as it is on Bob's side. So the universe kind of decides to create this number in two places at the same time. And at the same time, the universe guarantees that if there's anyone in between trying to eavesdrop, they will never get access to this number. So Alice and Bob have, for certain, knowledge that the number that they possess, only they possess and no one else possesses. And you can use that with some fancy cryptography to create a much more secure system. And in fact, kind of the visualization, the visual we have of an ultra-secure internet using this kind of technology looks very similar to the one I had earlier, with a slight addition. Because now we have building 1 and building 2 connected not just through the internet, but through this kind of line that goes to some boxes labeled Q. Q for quantum, because I am not very creative sometimes. And what those quantum boxes do is they realize exactly this protocol, and they allow the people in that building and people in that building to scramble and unscramble the data in such a way as so that anyone who is eavesdropping in between, well, they might be able to store it, because same thing, but that data is scrambled in a way that nothing could ever break into it, no matter how long it takes, no matter if you have supercomputers or quantum computers or some technology that we don't yet know about. And this creates a step change. It creates a situation where we can now have kind of bulletproof